Great, thanks, Jenny. Yes, I'm Erin Towler from NCAR, one of the PPAI panel members, and I get the pleasure of introducing Doug Smith, who is a Met Office Hadley Center Research Fellow, who's working on seasonal to decadal climate prediction. He joined the Met Office in 1997, developing the Met Office Decadal Climate Prediction System, and leads the Decadal Predictability team since 2008. His research examines the drivers and predictability of seasonal to decadal climate variations, and he helped to uncover the signal-to-noise paradox that he's going to be talking about today. He previously co-chaired the WCRP Working Group on Subseasonal to Interdecadal Prediction and the WCRP Decadal Climate Prediction Panel, is a member of the WCRP Grand Challenge on Near-Term Climate Prediction, and co-chairs 2 Coupled Model Intercomparison Project 6 activities, the CMIP6, the Decadal Climate Prediction Project, and the Polar Amplification Model Intercomparison Project. So thanks, Doug, for joining us today, and I'm going to hand it over to you.
Okay, thank you very much, and welcome everybody. Thank you for coming to this seminar. Yeah, so I'm going to talk about the signal-to-noise paradox. You may have already heard about this. We had a talk on this last time, which was very interesting. So the take-home messages from this talk, it's a tale of 2 things really. The good news is that North Atlantic climate is much more predictable than we previously thought. And the bad news is that there is a serious deficiency in climate models that affects particularly atmospheric circulation. Okay, so if we look at projected 30-year trends in North Atlantic climate, then we find, looking at climate model simulations, we find huge uncertainty. So this is illustrated by this paper by Clara Desser that shows 2 different ensemble members from the NCAR Large Ensemble. It's 30-year trends, and the colors represent temperature and the contours represent sea level pressure trends. And you can see that these two different ensemble members effectively show the opposite signals for European temperature trends. So one has cooling over Northern Europe and Scandinavia, and the other one has warming. And that's because the North Atlantic oscillation, the sea level pressure pattern, highlighted by the contours here, is opposite in these 2 different ensemble members. So this suggests that there's a huge uncertainty in these projected for 30-year trends. And since these projections only differ by tiny perturbations in the initial state of this climate model, then the conclusion from this study is that this uncertainty is irreducible because we could never initialize such tiny perturbations. We'd never know the real world to such accuracy. So if we look at decadal climate predictions and treat the models at face value, then we would arrive at the same conclusion. So what I'm showing here is the black line is the observed 8-year running mean North Atlantic oscillation, NAO. And the thick red line is the ensemble mean of decadal predictions from CMIP5 and CMIP6. There's 169 different ensemble members from 14 different models. And you can see that the ensemble mean shows very little signal at all. And the ensemble spread, shown by the pink shading, covers most of the observed range, such that internal variability in these model simulations pretty much covers the observed range. I mean, indeed, we can find. So if we look at this peak in the NAO in the early 1990s, we see a very strong signal in the observations with warming over Northern Europe and cooling over the northeastern US and Canada. And we can find some ensemble members that have that similar signal, and we can find some ensemble members that have the opposite. So just as for the 30-year predictions, there appears to be very little predictability on this timescale if we take the models at face value. But of course, decadal predictions can be tested more thoroughly because we have the observations to compare them with. And so the left-hand plot then is the same as I just showed you on the previous slide. And the right-hand one is the same as the left-hand one, except that the variability in the ensemble mean has been scaled to match the variance of the observed time series. And now you can see that actually these decadal predictions do have a signal that matches the observations and has a very high correlation. The correlation is 0.8. But there's a discrepancy here because a correlation of 0.8 should explain, over 60% of the observed variability. And clearly, if we look at the raw model output, then this variability explained by the ensemble mean is just a tiny fraction of the observed variability. So the magnitude of the ensemble mean variability is inconsistent with this high correlation. This means that there's little agreement between ensemble members. And because of this discrepancy, we cannot treat ensemble members as alternate realizations of the observations. So this has been seen before in seasonal forecasts. It was first found in seasonal forecasts of the NAO. And we called it the signal-to-noise paradox, and I'll explain why now. So if we plot for seasonal forecasts of the NAO, if we plot a graph of the skill in terms of the anomaly correlation between the ensemble mean forecast and the observations versus the number of ensemble members that go into the ensemble mean, then we find a curve like this where the ensemble, where the skill increases steadily as we add more ensemble members. And that's expected because adding more ensemble members reduces the noise, and we expect to get a higher predictability by doing that. But what's not expected is this blue curve down here, which is if we replace the observations with one of the model ensemble members and then use the ensemble mean of the remaining members to predict that individual member, we find that the skill for the model predicting one of its own members is much lower than for the model predicting the real world. So this is a bit of a paradox because obviously the models are a perfect representation of themselves and an imperfect representation of the real world. So we would expect logically for the skill to be better for the model predicting itself than predicting the real world. So this means that individual model ensemble members cannot be treated as alternate realizations of the observations. It also shows that we need a very large ensemble to extract the predictable signal by taking the mean of a very large ensemble. You can see the skill grows as we add more ensemble members, and it really undermines the basis of ensemble prediction. So although we call it a paradox, the interpretation is fairly simple. So you can imagine that there is, in some hypothetical case, there is a predictable signal shown by the red sine curve in this schematic. And on top of that, there will be some noise such that the observed variability will look like this black curve, for example. The total variance, sigma squared, is greater than the variance of the actual predictable signal, sigma s squared. So if that's what the observations look like, then our interpretation is that the models look more like this plot on the right, where we have a much smaller predictable signal and a lot of noise on top of that, such that the total variance is about the same as in the observations, but the fraction of that variance that's actually predictable, the signal, is much smaller than in the observations. So we can actually quantify this error, and we called this the ratio by computing the ratio of predictable components. So in the observations, the predictable component can be estimated. We can't calculate it exactly, but it can be estimated from the correlation that we're able to achieve between model forecasts and observations. And we expect the real predictable components of the observations to be bigger than this anomaly correlation, because this is what we're able to achieve right now with imperfect models. So if the models were better, then we'd expect to get a higher correlation. But this is an estimate that we can use for the moment. In the model world, the predictable component can be calculated as the standard deviation of the ensemble mean. Remember, it's the ensemble mean that contains the most predictable part of the signal. So we calculate the standard deviation of the ensemble mean, and we divide it by the total variability, the total standard deviation measured over all of the ensemble members. And then we just take the ratio of those two predictable components to calculate the ratio of predictable components like that. We can refine that slightly further to calculate the ratio of predictable signals. And it turns out that if the total variability in the observations and models are about the same, then the ratio of predictable signals is actually equal to the ratio of predictable components. Hope that makes sense. Okay, so we go back to our time series plot. On the left, again, the raw model output. On the right, the variance adjusted. What you can see here is a fainter line with lots of noise on it. this is the ensemble mean of the 169 ensemble members. Although it does have a significant correlation with the observations, there's clearly still plenty of noise in this time series, unphysical noise. So to smooth that out, what we did was we took forecasts from the preceding 4 years, so 4 years worth of forecasts, but all using previous information. And that's what we get with the thick red line now. And this has got nearly 700 ensemble members in the forecast. And as I said, we calculate this ratio of predictable components, and we find that it's actually 11 in this case. And since the variability in the models and observations is about the same, then this is the error in the predictable signal. So it says that the signal is an order of magnitude too weak in the climate model ensemble. Now this is a real problem because it's the error variance that decreases linearly as we add more ensemble members to squash out the noise, and so an error in the signal and the standard deviation equates to of a factor of 10 equates to a need for 100 times more ensemble members to extract the signal. Okay, so having defined what this ratio of predictable components, this RPC, is, we can actually see how widespread a problem it is by plotting maps of the RPC on decadal timescales. So this is years 2 to 9 of these decadal prediction systems, and I've plotted maps of RPC for temperature, precipitation, and sea level pressure. And what you can see is that for temperature, there's widespread. So anywhere where this plot is red shows where the RPC is greater than 1, so showing that the predictability in the real world is greater than the predictability in the model world. This kind of unexpected situation. So you can see that for temperature, most of the globe is actually greater than 1, and significantly so. And then if you look at variables that are more affected by atmospheric circulation, so precipitation and sea level pressure, then you can see that these red colors become stronger, such that, for example, for Sahel rainfall and for especially the nodes of the North Atlantic Oscillation, then there's a very clear and high values of the RPC in those regions, really consistent with the fact that the atmospheric circulation signals are too weak in the models. So as I said, this was first of all spotted, this error was first of all spotted in seasonal forecasts of the NAO. And it's not just confined to one modeling system. So this plot from Laura Baker's paper shows the RPC versus the ensemble size for several different operational forecasting systems. And they all, apart from one, follow this curve where the RPC increases to values greater than 1, and even up to maybe around about 3 for seasonal forecasts of the NAO. The only system that it doesn't follow this is the ECMWF one, but then that's the only system that doesn't have significant correlation skill for the NAO itself. It's been seen in other contexts in seasonal forecasting. So this is for summer European rainfall. Again, if we look at the raw model values, where the dots are individual ensemble members and the red line is the ensemble mean, and the black line is the observations, and you can see very little variability in the ensemble mean and a very large spread in the individual ensemble members, suggesting very little predictability. But actually, in this case, there is a significant correlation, nearly 0.5. And if we rescale the forecast, you can see that some of that variability is actually captured by the ensemble mean. So in this case, the RPC is equal to 5. And then this paper by Steve Yeager, they calculated the RPC in Sahel rainfall predictions. I can't remember, I think this is for years 1 to 5 or something like that. And so if you plot the raw model output, again, you see very little signal in the ensemble mean compared to the variability of the observations. But if you rescale that, you start to see that the signal is actually much more convincing in the ensemble mean. So the red is the initialized forecast ensemble mean, and the RPC in this case is 2. It's also seen on subseasonal timescales. So this paper shows the teleconnection, the MJO teleconnection. So you can see that there are teleconnections in the North Atlantic region between the NAO, between the MJO and the North Atlantic region. And this is the strength of this teleconnection in the observations, the top plot, whereas in the model simulations, none of them achieve the same strength of this observed teleconnection. This doesn't necessarily show that there's a signal-to-noise error, but it's at least consistent with that. And then this other study by Daniela Dominson really does calculate the RPC specifically for subseasonal forecasts, and it shows the RPC for the zonal wind in the Atlantic at 60 north as a function of time, so days into the forecast, lead time, and pressure. And what you can see from this is that so values of RPC greater than 1 are highlighted by the red, and you can see that this RPC error begins in the troposphere and appears to, propagate upwards into the stratosphere, if anything. But at least it's, what this paper does show is that it's also seen on subseasonal timescales. It appears after about 10 days. There's also evidence that the model's response to external forcing factors such as volcanoes and solar forcing could be too weak. So the left-hand plot shows a multi-model ensemble mean response to 3 volcanic eruptions, Agung, El Chichon, and Pinatubo. The colors show the temperature response following in the first winter following the eruptions, and the contours show the zonal mean, zonal wind response. And what you can see is that the models simulate about the right magnitude of the temperature response, but the zonal mean, zonal wind is much weaker in the models than in the observations. And then if we look at the response to the 11-year solar cycle, what we see in the observations is a fairly significant response with a lag of about 3 years. And what we see in the model, so this is a response in sea level pressure following a solar maximum. And what we see in the model simulations is a weaker response with no lag. And this lag could be, the fact that the response could be imprinting itself in the ocean. And if it's too weak in the models, then we wouldn't expect that imprinting to occur properly. And then, so most of the results I've shown for the predictions were from initialized predictions, subseasonal to decadal timescales. This study by Jeremy Clavand et al. Shows that the problem is also seen in uninitialized historical simulations. So again, it's a plot of the NAO anomaly. The black is the observations, again 8-year running mean, and the red is the ensemble mean of a large ensemble of uninitialized simulations. And they find a significant correlation between the uninitialized simulations and the observations. And again, they show that if you plot the correlation skill versus number of ensemble members, you find that the model predicting the real world its skill is higher than the model predicting one of its own ensemble members. And there have been other studies like the talk we saw last time where this error has been seen in uninitialized simulations. Okay, so the model, this error directly affects the NAO, but it also affects the impacts of the NAO. So in this talk, so we're going to look at this peak in the NAO period in the early 1990s, and in the observations you can see this quadrupole pattern where we're getting a strengthening in the westerly winds, leading to warming over Northern Europe and cooling over Southern Europe and Northern Africa, and a quadrupole pattern consistent with the atmospheric circulation pattern that we're getting there. But if we look at the ensemble mean of this large ensemble of decadal predictions, then we really don't pick up that pattern. That's kind of expected, given that the signal in the NAO is too weak. We know that already from these model simulations. But even if we standardize the model simulations now, we don't see anything particularly convincing compared to the observations. And that's because the ensemble mean really contains the greenhouse gas forcing, but the impact of the NAO, the changes in atmospheric circulation, are way too weak in this ensemble mean, and it's not really seen. But one way that we can overcome that is what we call NAO matching. So what we do here is we look for ensemble members that have the right magnitude of the NAO, and we diagnose the magnitude of the NAO from the ensemble mean forecast, but rescaled to match this RPC error. So effectively, we take the ensemble mean forecast, we multiply it by the RPC, which is essentially 10, and then we look for those members within the ensemble that have an NAO equal to 10 times the ensemble mean. And if we just take those members and then plot them, then we see that we do then regain the impacts of the NAO. And these ensemble members, of course, include greenhouse gases as well. So ideally, these would contain all of the predictable signals. So it's interesting to see what that technique does to forecast of the ocean as well. So what I'm showing here on the left is the raw model output in terms of forecasts of the Atlantic multi-decadal variability, AMV. We know that this is skillfully predicted in decadal predictions. In fact, it's one of the most skillful things that is predicted in decadal predictions. You know, that's been shown by many studies. But actually, it's not perfect. And if you look at this time series, again, the ensemble mean is shown by the red curve and the observations by the black curve. You can see that the timing of the minimum in the AMV is not really picked out that well by the ensemble mean forecast, and there's still a lot of uncertainty. But if we do this NAO matching technique, where we pick the ensemble members that have the right magnitude of the forecast NAO after adjusting for the weak signals, then we find a better forecast of the AMV. So the conclusion from this really is that the NAO skill is not driven solely by the AMV, because the AMV predictions themselves are improved when we select some of the atmospheric ensemble members that have the right NAO. Okay, so what are some of the implications of this error? So it means that error estimates based on the magnitude of the variability will give incorrect estimates of the forecast skill that could be achieved with an adjustment of that magnitude. And if we treat the ensemble at face value, so many probabilistic error estimates look at the number of ensemble members, for example, that exceed a certain value, a tercile, for example. And if the variability is underestimated in the ensemble mean, then these probabilistic error measures will give inaccurate results too. Now, in seasonal forecasts, you may have heard that seasonal forecasts of El Nino, particularly in the tropical Pacific, are overconfident. So this is the opposite problem to the one I've highlighted in this talk. And this has been known for a very long time. And in fact, there's been many attempts to improve this error, and one of these is stochastic physics, which is often used to try to increase ensemble spread. But in fact, in this case, stochastic physics may potentially exacerbate this problem where the models are underconfident. Previous studies have often tried to assess upper limits on predictability in so-called perfect model experiments, where we use models to predict its own evolution. So we generate a random ensemble and we try to predict the original evolution of the model. And this was often claimed to be an upper limit on predictability because the initial conditions in this case are perfect. But as we showed in this case, the models can be better at predicting the real world than at predicting themselves. So this no longer gives an upper limit on predictability. Event attribution may give inaccurate estimates of the probability of extremes if the models do not respond properly to, for example, the SST pattern that could be controlling the particular atmospheric anomaly in that case. And estimates of irreducible internal variability, like I said, like I showed right at the start of this talk, could be inaccurate, if the signal-to-noise ratio is too weak in the model simulations. And then models may underestimate the frequency of extreme events associated with atmospheric circulation if they don't generate the correct changes in atmospheric circulation. Okay, so what could be causing the signal-to-noise paradox? So there have been several papers trying to address this issue. One of the first ones was that it's all just noise. I think that's probably one that we can dismiss now, given that we have seen it in so many different contexts here, from sub-seasonal to seasonal, multi-annual, decadal forecasts, and in uninitialized simulations. So I don't think it's just noise. There was a study suggesting that the QBO teleconnection could be too weak, but then that wouldn't affect forecasts in the summer. So for summer European rainfall or for Sahel rainfall, for example, wouldn't really explain the error in that case. It could be a lack of persistence, errors in transitions between regimes, and errors in ocean-atmosphere interactions. These are all possibilities. But I wanted to highlight one hypothesis is that the eddy feedback in models could be too weak. So this was put forward by Adam Scaife in a paper. And so the plot here shows the eddy momentum flux, the error in the eddy momentum flux convergence in the Met Office model, seasonal forecasting model. So negative values are where the eddy momentum flux convergence is too weak in this model. And then the plot on the right gives a hint that increasing the atmospheric resolution may resolve this problem eventually. So this is a plot of eddy feedback strength versus atmospheric resolution from 150 kilometers on the right down to 10 kilometers on the left, compared to reanalysis. And you can see that the reanalysis values of eddy feedback appear to be stronger than in the model simulations. And there's a hint, although there's a lot of noise on this, but there is a hint that as the model resolution decreases, then maybe there is a stronger eddy feedback. But even at 10 kilometers, it's not clear that we've quite resolved it enough, and we may well need even higher atmospheric resolution than 10 kilometers. And then just finally, some further evidence that eddy feedback could be important comes from simulations of the atmospheric response to Arctic sea ice loss, future Arctic sea ice loss. So this is from a large ensemble of simulations from the Polar Amplification MIP, PPAI MIP, where the response to Arctic sea ice is diagnosed from many model simulations. We have 16 models contributing to this. So the y-axis in this case is some measure of the mid-latitude weakening of the winds, if you like. So the higher this zonal wind response index, the stronger the weakening of the mid-latitude winds as we reduce the Arctic sea ice. So all the models do show a weakening of the mid-latitude winds, but you can see that there is a relationship across these models between the strength of this mid-latitude weakening of winds and the eddy feedback parameter diagnosed from these models. And then what's particularly interesting is that when we diagnose the eddy feedback parameter from reanalysis, we find that it's actually larger than in all of these model simulations. So this shows that the eddy feedback appears to be too weak in models. And in the case of the response to Arctic sea ice, it suggests that the response would be at the upper end of the model simulations. Okay, so that's pretty much it. So I'll just summarize. So I think there is widespread evidence that climate models underestimate signals, especially atmospheric circulation signals. I showed examples on multiple timescales, sub-seasonal, seasonal. It's been seen in interannual, multi-annual, and decadal timescales. It's seen in different seasons, winter and summer. It's seen in different variables, temperature, rainfall, and pressure. It's seen in different regions. On seasonal timescales, it's not really seen in the tropics, but as you go to longer timescales, then it appears to affect the tropics as well. Especially, I showed an example for Sahel rainfall. And it appears to be caused by or simulated in response to multiple different drivers, internal variability, solar volcanoes, possibly greenhouse gases. So this has important implications, especially for regional climate projections. For example, I showed that the decadal predictions, the NAO signal, appeared to be 10 times too small. So, should we multiply projections of the NAO by a factor of 10? And if we did, that would give a very different picture to the current very weak signals that we see in climate projections. And what are the implications for attribution? On these kind of decadal timescales that I'm particularly interested in, there are several potential drivers: greenhouse gases, aerosols, solar, volcanoes, ozone, land use, etc. And I'm arguing that we can't really take the models at face value. So what we need to do to unpick this situation is we need large ensembles of single forcing historical simulations, so that we can actually diagnose the forced response to each of these different forcings, and then put that all back together to see how well we can, how much of the observed variability we can actually explain by a combination of these different forcings, taking into account that their magnitude may be too weak in the model simulations. And this is what we're trying to do with this WCRP Lighthouse on explaining and predicting Earth system change. So that's pretty much it. Thanks for your attention. I'm happy to take any questions.
Thanks, Doug. That was great. I think while people start thinking about their questions, I was just going to ask you one, and it kind of relates to the implications for regional projections. I know that the Met Office is doing some experimental operational, predictions using these, exact simulations. How does the signal-to-noise paradox make you kind of rethink that, or how do you caveat that when you're putting those out for consumption, experimental consumption, but for the community?
Sorry, Erin, can you? I was just reading the question in the chat. Can you repeat that one, please?
Yeah, I didn't. Okay, yeah, I see there's one in the chat, but I'll just kick us off with, yeah, how does this influence how you guys are doing? I know the Met Office puts out operational experimental forecasts using these predictions. I mean, how does the signal-to-noise paradox kind of make you rethink or reframe how you put those out to the community?
Yeah, so that's a good question. So at the moment, we just put out the raw model output. And so ideally we would adjust that and recalibrate it based on the signal to noise error. And that's something that we hope to do in future. But at the moment, we do just, look at we present the raw model output, but when so we make this global annual to decadal climate update. And when we interpret the model output, we do allow for the fact that the signals could be too small. And so some of the things that we highlight in that, for example, changes in the NAO, do take into account this potential error.
Great, thanks. Looks like Matt has a question in the chat. Matt, if you'd like to just say it, that might be simpler, or I can read it if you.
Sure, I'll just read what I wrote. Counter-argument expressed, for example, by Weisheimer and EC collaborators is that the hindcast records are mostly too short, so that longer hindcast records, such as their recent centennial version with the SEAS 5, there's a paper published in BAMS, and I know there's a newer version now where they're running out forecasts out to 2-year lead times, in fact, going back to 1900, all initialized with the Sarah 20C. That these longer hindcast records do have RPC records, values that are much closer to 1. So in other words, their argument is that there is no signal-to-noise paradox, just that there are very large decadal variations in skill, so that you could have periods of time, say for the NAO, where you were basically lucky, where your skill was higher than the predictability, or alternatively that there are long-term variations in predictability on decadal timescales And then you would need to really sample that well in your model to be clear that you were not essentially looking at one regime where the forecast situation was lying in a different one. That's at least their argument. So what is your response to that?
Yeah, I mean, it is possible that skill could vary in different periods. That's certainly possible. I would caution that some of their differences in skill in different periods don't appear to be very significant. And they're not always seen by all of the models. So some models, for example, don't show the same lower periods of skill. And in terms of whether the models can be underestimating the atmospheric circulation response, I think, you know, it is seen in such a wide range of across different timescales that I think there is a real physical error in the climate model simulations. And then when we back it up with these estimates of eddy feedback that appear to be too small in all of the models compared to observations, I think there is an issue here to be addressed.
I mean, I'm certainly willing to believe the models are poor. I don't think I'm going to yield to anybody in my view on that. But I mean, most of the hindcast records do not really go back prior to about 1960. Theirs is really the only effort that goes back that far. We've been doing something similar with the model analogs, but that works better in the tropics. And certainly one does see in their analysis very large swings, and in particular a very pronounced minimum in skill that makes it look like, you know, the recent era is either been more predictable or we've been somewhat more lucky.
Yeah, I mean, there could be something in that. And we definitely need to look at it in more detail. And we also need to understand better what could be driving, you know, the skill in these externally forced simulations, the apparent skill there, you know, or what, at least what's driving those signals, you know, which is where this WCRP Lighthouse activity, I think, is going to be important for understanding what does drive decadal variability on these different, in response to these different factors.
I don't see any other questions in the chat, but as people think about it, maybe you could explain what this WCRP Lighthouse activity is. I don't know that everyone's familiar with that.
Okay. Yeah. So the WCRP has been reorganized recently, and as part of that reorganization, there are these Lighthouse activities to kind of encourage people to focus on different areas. So there's one on safe landings for climate. So, you know, how do we, you know, get climate change under control? There's one on my climate predictions. So how do we get the most useful local information from climate model simulations? There's one on digital twins, for example. And this one is particularly aimed at explaining and predicting multi-annual climate variability and changes. And so as part of that, we're aiming to build an operational attribution system such that when we make a decadal forecast, we'll know what it is that's driving that forecast. Is it purely internal variability, or are there changes in aerosols, for example, that are playing a role? All of those different things. And if we can understand what's actually driving the forecast, then we can have a much better idea of whether we believe it, basically. Because if we don't believe, you know, if it's very sensitive to things that are uncertain, such as aerosol changes, then maybe we'd have less certainty in the forecast. And we think the way to do that, this operational attribution, is to or one way to do it, and the way we're trying to encourage many people to do, is to do these large ensemble single forcing experiments. So we run the historical period forced by only a single forcing at a time. So greenhouse gases, aerosols, solar, volcanoes, etc. So these are DMIP experiments that have already been proposed, but our take on that is that we need very large ensembles. So I'm talking about 50 ensemble members ideally, so that we can squash out the noise and work out what the real simulated signal is for these different forcing factors.
Great, thank you. I saw that I'm sorry, I'm going to mispronounce your name.
Yeah, Qinghua.
Qinghua, can you go ahead, please? Thank you.
Yeah, so this is a very interesting talk. So I also have some impression when I just analyze my model result. I find that just if you look at global average, the data, the model show pretty good consistency with observation, like the global warming over like the decade something. But if we look at the regional feature, the model always fail to capture like the circulation pattern. So my question is that, do you think that our model generally have too high sensitivity or overestimated the sensitivity to the global warming or like the anthropogenic forcing, and less sensitivity to something like the dynamical circulation change, something like that? Because the reason I ask this is that my understanding is that most model center, when they develop their model, they try to evaluate to justify their model by compare like the observation with the example mean. But in that way, somehow they assume all the observed record is CO2 driven. So, but the model, if model cannot capture, they just tune their model to fit the two curve. So it's my just a really wide guys. So I just wonder, what do you think about how we are confident about our model sensitivity to is the anthropogenic forcing or like the any external forcing or internal variability? It seems like to me it's like a black box, and we still have a long way to go to figure this out. But I just want to hear your opinion on that.
Yeah, that's a very interesting question. So to first order, the changes in atmospheric circulation, shouldn't have a big impact on global mean temperature. But I think to second order, they could affect some of the variability. They could potentially drive changes in the ocean that would give, changes in decadal trends, for example, in global mean temperature. So I do worry about using the observed kind of warming trend to constrain the climate sensitivity, especially if that's just based on global mean temperature, when actually we know that in the period there were very large regional changes, especially in the Pacific, that have been contributing to to the changes in global average temperature. So I personally, I think we should pay more attention to the regional patterns that are simulated by the models and see if in fact some of those do match or could match. This is why we need these single forcing experiments, really, in my opinion, because it is possible that, for example, volcanoes or something like that could, or aerosols, papers have shown that aerosols can affect the Pacific temperatures, so the IPO, the PDO, that sort of thing. And if those signals are not simulated strongly enough in the model simulations, that because they could be driven by atmospheric circulation, for example, then there's a possibility, in my opinion, that they could be more strongly externally forced than we currently think. In which case, constraining the models just based on global average temperature may be missing some of this variability that is actually externally forced. Hope that makes sense.
Thank you.
Looks like there's a question from Bao in the chat, but he also says hand raised if you want to just ask your question.
Yeah, hi, Doug. Thank you very much for very interesting talk. So I have kind of a very general question. You have mentioned many factors can influence the signal to noise paradox, such as ensemble size, lead time, model mean states, probably also model initialization. So this seems to be very complex. So from modeler perspective, what's the most practical way to solve or deal with this problem?
How to deal with the problem? Is that your question?
Yeah.
Okay. I mean, although it highlights a model error, it does have the upside that you know, the predictability appears to be much higher than we previously thought if we took models at face value. And the way to extract that predictability is to get rid of the noise by using a very large ensemble mean of a very large ensemble. That gives you the signal, and then to compare that signal with observations, ideally with a long time series, so that you can diagnose whether that signal is really too small. But, you know, for example, by calculating this ratio of predictable components that I highlighted. And then if it is too small, then you can be justified in, you know, boosting that ensemble mean signal to match the predictable variance that you think is really there. And that's one way that I think we can use models at the moment. It means that we, you know, basically need a much larger ensemble than we should do. And the example I showed for the decadal predictions, if the signal is 10 times too small, then we need 100 times more ensemble members, unfortunately, than we should do. But I think that's one way that we can do, and indeed we do that every winter. We make seasonal forecasts of the NAO, and by and large, those have been pretty successful so far. Does that answer your question?
Yeah. That is when we also mentioned the stochastic physics, and that is another possibility.
Well, so when I mentioned stochastic physics, I was actually arguing that doesn't help this particular problem. It may help when the models are overconfident, as they are in seasonal forecasts of El Nino itself. But in this case, where the models are underconfident, then increasing the spread through stochastic physics, it could make it worse, actually.
Okay. Yeah, thank you.
Great. Next, Zhu Wang.
Yes, thank you. Doug, thank you for the interesting talk. I have two questions. You showed increasing model resolution can strengthen eddy feedback and also enhance the predictable information. So it seems we have two approaches to enhance the predictable information. One is to increase the model resolution. The other is to increase the ensemble size. On this summary slide here, it seems you advocate a larger ensemble size over higher model resolution. Could you share your thoughts on that? Also,
yeah.
I also have a second question. It's related to the second bullet point here. In regions where we have both like ENSO impacts and NAO impacts, we would have to deal with both overconfidence and underconfidence issues. How do you handle that for regional projection? Thank you.
Okay, so the first question was about resolution versus ensemble size. So if I go back to this plot here, where, you know, there is a hint that at higher resolution we get a stronger eddy feedback. But the problem is that even at 10 kilometers resolution, which we can't even afford to run in climate model simulations at the moment, nowhere near, you know, it doesn't seem to be high enough resolution to really resolve this problem. And in fact, we've rerun our whole seasonal, so the standard seasonal forecast resolution is 60 kilometers or 50 kilometers, and we reran the whole set at 25 kilometers and didn't find any improvement in the skill of the NAO. So if resolution is to be the answer, then it appears to be that we need, you know, even more than 10 kilometers potentially, which we at the moment we can't afford that. So the present day solution, I think, is to increase the ensemble size to diagnose the predictable signal. There could be another solution if we could understand what really caused, what's really at the heart of this problem. Maybe there's a way of parameterizing it, but that's a little way off. And now I've forgotten your second question, sorry. What was the second one?
Second one is how do you deal with the overconfidence and underconfidence issues
Okay.
at the same time?
Right. Well, I think you need to consider what it is that you're actually trying to predict. So, for example, if we're predicting the NAO, then although El Nino is overconfident and does affect the NAO, what we can diagnose is the actual NAO predictions themselves and show that they are underconfident in the models. And so, I think that's the way around that, to look at the actual thing you're interested in and directly diagnose whether it's overconfident or underconfident by calculating the RPC for that particular variable. Does that make sense?
See if we consider like precipitation or temperature over US East Coast, which is affected by both the ENSO and the NAO. The ENSO is the overconfidence and the NAO has the underconfidence issue.
Yeah.
So how would you deal with that?
Well, the models would simulate some combination of overconfidence to ENSO and underconfidence to NAO, and they would give you forecasts of precipitation, for example, and then you would assess those forecasts, calculate the RPC for those forecasts, and it would either be greater than 1 or less than 1, and if you adjust your forecast appropriately based on that.
Okay, thank you.
Great. And Hyan, looks like you have your hand raised.
Thank you, Doug, for the nice talk. And I have some practical questions. I would expect that variance adjustment will become a very popular approach in climate prediction field. And I wonder whether you could give us some advice, what cautions we need to take when we do the scaling or adjustment of variance. And also, similarly, for detection attribution work, there will be a lot of questions about models, signal noise. It's all about signal noise ratio. And now, if we look back to all the research in attribute detection and attribution, how do we need to think again and say, hey, you probably need to worry about signal noise ratio problem?
Okay. Remind me the first one again. Sorry.
The first question is,
I
wonder whether you could give us some advice, what cautions we need to take when we carry out variance adjustment.
Yeah, okay. So what you don't want to do is just scale the variance of the ensemble mean to be the same as the observations. That would only be right if the ensemble mean, if there's perfect predictability, because there's no noise in the observation. So what you need to do is calculate the predictable fraction of the real world that's predictable, the fraction of the real world variance that's predictable, and the error in that fraction that's in the model simulation. So the RPC gives you the ratio of these predictable components, and I didn't go into this, but it is an underestimate of that ratio, because one reason is because the numerator in that RPC calculation is the correlation with the observations, and we would expect that to be an underestimate of the true predictable component of the observations, given that we can achieve that with imperfect models. So the way that we did it was to calculate the error in the predictable signal and scale the ensemble mean by that error effectively. So that effectively meant boosting the ensemble mean NAO signal by a factor of 10 or 11, I think it was, for these decadal predictions. So that, I think that's what you need to do. But of course, there will be, there are uncertainties in that, which we should take into account more. There's observational uncertainties, and there's just uncertainties in in the calculation of this RPC. And then there's additional factors that Matt highlighted in that there could be different different periods when the skill is higher or lower, for example. And then your second question, what was that one again?
How should we rethink about attribution studies and the future if we say if we review an attribution paper, and would we do we need to worry about the signal noise ratio problem in the models and say, hey, you need to redo your work and by adjusting the variance?
Well, I mean, in my opinion, yes. I think there's a fair bit of evidence that this could be an issue, and if we don't even, acknowledge it, then we could be missing something important. So I think this is something we really need to, we don't know all the answers at the moment. We don't know the impacts on, long-term projections, for example. So this is an area that we really need to look into now, I think, in great detail. And I do want to stress the need for these large ensemble single forcing simulations, really to pick apart what the different external forcing factors really do to atmospheric circulation, and then try to explain, see how much of the real world we can actually explain with a combination of different forcing factors. At the moment, we tend to put all the forcing factors in one simulation, and then anything that we can't explain, we attribute to internal variability. I don't think that's the right approach to do this problem.
Thank you, Doug.
Okay.
Thanks, Doug. I think we're nearing the end of the hour, so I'm going to pass it back to Jenny, but thanks for a great talk and a great discussion.
Thank you.